Now, let's try to talk about the ideal Otto cycle analysis based on what we learned about the whole processes of the ideal Otto cycle. So for today, instead of going quite through really boring equations, then I'm going to directly implement this example. I'm trying to solve the example problem that you see now. Then, in order to solve this example, then I'm going to show you what equations we have to use to do those kind of thermodynamic analysis for the ideal Otto cycle. So please read this statement very carefully, and I'm going to try to solve this example. Please pause the video and read this statement. All right. So I hope that you already have read this statement. Then let's take a look at this example. Now, based on those given conditions, then we want to solve the temperature and pressure at each state, which is the key to solve other following questions. The second one is we want to calculate the net work output. And the next one is that we want to also calculate the power output. Then we will solve the thermal efficiency of this specific ideal or the ideal Otto cycle. And the last one is we want to calculate the mean effective pressure for the cycle. I'm going to explain what that mean effective pressure means in later slides. Okay, so don't hurry, and then let's see when we have to solve this one. Now, in order to solve this problem, let's assume that your engine is an ideal Otto cycle. And let's try to use the cold air standard assumption, which means that air is an ideal gas and its specific keys are constant at room temperature. In the case, let's use these specific keys that are given in this statement. Now, there are several given conditions. The first given condition is that we are talking about 4-cylinder gasoline engine. So gasoline engine is basically the same as a spark ignition engine. And that engine runs at 4,000 RPM. And I'm going to use this number later when you try to calculate the power. And geometry is given. So we know the displacement volume, which is 1.6 liter or 1.6 times 10 to minus 3 meter cubic. And we also are given the compression ratio. Now the compression ratio is 8. We are also given the heat input amount, which is 800 kilojoule per kilogram. We also know the pressure and temperature at the start of this cycle. So now the pressure at the beginning is 100 kilopascal and temperature is 17 degrees Celsius, or in the absolute temperature unit, that is 290 Kelvin. So now from those given conditions, let's try to solve this problem. Before we talk about how we can calculate the temperature and pressure at each state, now let's try to solve certain parameters that we can calculate from the given conditions. I already wrote down those given conditions, such as displacement volume, the pressure and temperature at the first state, and also the specific heat ratio, K value, and the gas constant of the air. Now, from the displacement volume, what we do know is displacement volume is basically the difference from the maximum volume and the minimum volume. Now, the maximum volume should be same as the volume at the first state, because now at the first state, before the compression, your piston should be at the bottom dead center. Okay. Now, the minimum volume or clearance volume should be after the compression process, which is at state 2. So now we can write the equation about the displacement volume in terms of the difference between the initial volume and the after compression volume. And now, what is this? How can you express the same equation in terms of this specific volume? So now we should have m, the mass of the air or working fluid inside your engine, times specific volume minus and specific volume at state 2. All right? So if you do know V1 and V2, then from this equation, we can calculate the mass of the working fluid or the air inside of your engine. Now, how can you calculate the specific volume at V1 and V2? The answer is yes, we have to use the ideal gas law, because at the first state, we know the pressure and temperature. So, because we already assumed that your air is an ideal gas, we can calculate V1, the specific volume, to be RT1 divided by P1. So we can calculate the specific volume, which is 0.8323 meter cubic per kilogram. All right. Then, how about V2? Can you calculate the specific volume at the state 2? Okay. I actually forgot to write another given condition, which is your compression ratio R is 8. Now, this compression ratio is defined as V1 over V2. Again, the ratio of maximum volume to the minimum volume. Because as far as we talk about the ideal Otto cycle, that is a closed system. So mass should be conserved by itself. So this compression ratio can be also written in terms of the ratio of specific volumes. Okay. So what does it mean is your V2, the specific volume after compression, can be calculated based on V1 over R. All right? So it gives us the equation, the number of 0.1040 meter. Right. Okay. So now we already could calculate the specific volumes at state 1 and state 2. And also, by having K value and R value, gas constant, we also can calculate Cp value and Cv. Right? So I'm not going to write this number for Cp and Cv, but you can find out the lecture note that I'm going to upload to Canvas with annotation. So you can please check the Cp value and Cv value, and try to practice yourself about how you can calculate Cp and Cv from given specific ratio and gas constant. So one more thing that I have to mention here is that so I'm going to talk about it in the last part of our lecture, but you can find out the exactly identical example problem in your textbook. Okay, but in that textbook, the author calculated, V1, and V2 based on the displacement volume, and he just simply ignored the portion of V2. So he calculated, mass as the ratio between Vd over V1. Okay. So that is a good approximation, because anyways, V2 is very small, but let's not use for now, because now we believe that we can actually calculate the more accurate value of M. Okay? So please ignore that portion of a solution in the textbook. Okay? And I'm going to mention the solution of the textbook later at the later part, the last part of this lecture. All right?